vector. And then you can see that if you take the first derivative of this dot product, then it will be 0 by using the René-Trident theta. And this says that your alpha s dot b naught is again a constant c. So alpha lies on the plane equal to c. Okay. Third one is that suppose so let small a okay, suppose that for a curve alpha, if all its tangent lines you have a regular parametric of alpha, and if all its tangent lines to the curve alpha pass through a fixed point, suppose small c, then we can assert that the curve will be a straight line. Okay. Just by constructing these tangent lines, that is, suppose you take a map yeah, 1 minute. So lambda goes to alpha s plus lambda s alpha dash. Okay. So at the point alpha s, and since a lies in since this vector c, this point c lies in every tangent line, so there exists a real number. This such that your c will be can be represented as alpha s plus lambda s alpha dash. Okay. So this alpha dash is your ts, so you can, so this is your ts. Now after differentiating both sides, you will get that ts plus so ts plus lambda s kappa s eta s. Okay, this is 0. Now taking dot product with t and eta, you will get, so taking dot product by t and eta, you get that. So taking dot product by t, you will get 1 plus lambda s is going to be 0, and taking dot product with eta, it will give you that lambda s alpha s is 0. So from the first equation, you will get into the fact that, so your lambda s will take the form minus s plus some constant, suppose small a. Okay, and therefore from the second one, so whenever your s is not equal to a, then your alpha s must be 0, right? But the fact is that then, and this implies we have, by using the continuity of this function kappa, you can actually have this is going to be 0 for all s. That means this is identically 0. And then by using the note 1, this one, therefore alpha turns out to be a straight line. So this implies alpha will be a straight line. Fine. And the fourth one, suppose consider a unit speed curve which is lying on a sphere of radius smaller. Suppose alpha be a unit speed curve lying on a sphere of radius smaller, then the curvature kappa will be at least reciprocal of r. This one. Okay. And you will see that if you are considering a circle, if you are considering a circle of radius r, then your curvature will be 1 by r. Okay, that you can check. And this fact can be proved just by using the property of the curve, that is, it is of unit speed. So since it is unit speed, so you will have that alpha alpha s dot ts, it is 0, and then differentiating this equation again, you will have, so it is alpha dash s ts plus alpha s t dash s equals to 0. Then by applying the definite formally you will have. So it is your ts dot ts, and from this one it is alpha s dot kappa s eta s, right? This one. So this is 0, and therefore your kappa s and alpha s dot eta s is 0. It is your -1. Okay. Now taking norm, you will have, so it is 1, and this will be less or equal to kappa s and yes. So this is norm of eta s, this one. Okay. Okay. So this is actually, this norm is 1, and this is R, right? This is, therefore your A will be greater than equal to this one. Yes. Okay. So the curve, so alpha be a unit speed curve lying on a sphere, radius r, and you need to take that this curve will have so d of positive curvature, right? Okay. Fine. Now, so now let us move to the case that if you start from a regular parametric curve having arbitrary parameter, then as we have already proved, it could be made naturally parameterized by the arc length parameter small s. So therefore, suppose you have so you can put a remark here. Let's start from a regular parameterized curve. Alpha, then you will get a curve mu from, I think I would like to put it beta, from j to r cube, which is naturally parameterized, by arc length small s, and alpha and beta are equivalent. Okay, and you can consider the change of parameter here. So the change of parameter, suppose it is phi from I to j, and with the help of this change of parameter, you can easily, we have already shown that the trace of alpha and trace of beta are same, and this provokes us to extend all the local concepts that we have already discussed for this kind of curve to alpha. That means if you want to define curvature of this alpha, of this one, suppose to define the curvature. Suppose we denote it by K kappa T of alpha at alpha T, for T belongs to I. So define this by means of the curvature of the reparameterized curve beta from Z to R cube. Okay, so by means of the curvature of beta, okay, which has been reparameterized by the arc length, that is small s is your phi t, right? And this definition and this, so we should note that this definition of curvature of the regular parameterized curve alpha having arbitrary parameter, so this is independent of the choice of beta, is independent of the choice of beta. And this shows that considering only naturally parameterized curve would not be essential in this context. So with the help of this definition, we can prove that for any regular parameterized curve, so we would like to get some kind of formula which will help us to determine curvature for any regular parameterized curve having arbitrary parameter. So that means, so this will be revealed through this theorem that suppose alpha be a regular parameterized curve in R3, then its curvature can be written as, it will be norm of alpha double dot cross product with alpha dot divided by norm of alpha dot cube, or dot denotes the differentiation with respect to the parameter t. Okay, and this expression can be achieved by means of this reparameterization of alpha, which is naturally parameterized by the arc length s. So suppose you choose a naturally reparameterized curve of alpha, suppose alpha bar. So the unit speed reparameterization of alpha in terms of the arc length parameter small s. Small s. Okay. Now, whenever we are executing differentiation with respect to the parameter small s, we denote it by dashed, and whenever you are executing the differentiation with respect to the parameter t, it will be denoted by dot. Okay. Okay. So then, so this says that, so this says that your alpha bar of S is alpha t, right? And from this, by differentiating with respect to the parameter t, you will get alpha bar dot by using chain rule. Okay, I put ds dt, and here you will have alpha dot, right? I think, I'm sorry. This will be,
Excuse me, sir. Hello.
yes.
Yeah.
Hello.
In this case, we take a unit speed reparametrization of alpha,
Right.
and then we take
Yes.
the dash.
Yes. Hello. Yes,
Huh.
alpha bar is a unit speed parameterization of
Unit
alpha.
speed
Yes.
reparameter. Huh.
Yeah. Yeah. I
তাহলে
think,
then kappa is equal to norm of um, uh, alpha bar double derivative alpha bar the second derivative.
this will be dashed actually. Yeah,
হ্যাঁ,
yeah.
it will be dash,
This
double
will be
dash.
dashed. It got, yes. Yeah. Thank you. Thank you. Thank you. So okay. So then by using the definition of the curvature, so your kappa will be by means of the unit speed parameterization. So this will be alpha bar double dash s. Yes. And I'm not going to compute all these calculations, so you can do on your own. So this will be this will be, yes. So it is something like this. So ds dt okay dot ds dt dot I think I should leave this as an exercise for tutorial session because I need to.
Sir, this is determine that the DDS of alpha dot by ds dt. Alpha double prime bar norm is equal to norm of alpha bar can be written as DDS of alpha alpha dot by ds dt.
Yes, it is true. That is, it is actually DDS of I think alpha bar dashed by something, can say, yeah.
Sir, alpha dot over
Not
S dot.
alpha bar dash set. Alpha prime alpha dot. Alpha prime.
Alpha dot over S dot.
Huh.
So I think we have to find alpha double dot.
Yes. So I think so it will be
So leave this for the exercise.
yeah, I think yeah.
Yes, sir. Yes, sir.
Yes, I think that would be better. Yeah. Okay. Okay. So after calculating these derivatives and all these things, you can get this result. I think it's very easy. I'm not. Yeah. Okay. Okay. So in a similar in a okay, then after defining this curvature for a regular parametric curve having arbitrary parameter, you can define the torsion for a regular parametric curve having positive curvature. So one can talk of the torsion of a regular parameterized curve without having singularity of order 1, that means having positive curvature. And in this case also, you can compute the torsion for arbitrary parameter, and it will be something like this. That is, it will be the alpha dot, something, yeah, taking with alpha triple dot by norm of dot cross this one. Yeah, I think it is okay. Yeah. So using these expressions, you can compute, you can evaluate the curvature and torsion for a very interesting curve, which is the circular helix. That means suppose, so I think I will leave this also as an exercise to find out the curvature and torsion. Of the circular helix that will be defined as so alpha theta, that means a cos theta, a sin theta, b theta, where theta is in between this one, and your a and b are constants. With, suppose you take a greater than 0. Okay. So you can compute these geometrical entities, curvature and torsion for this curve, and that will be interesting one. Okay. So if you take the ratio of curvature and torsion, so that will be a constant. Okay. Okay. So let's move to prove the most interesting theorem, that I have already said, that the fundamental theorem of space curves, right? It is a fundamental theorem of S curves. So this gives you this reveals the fact that the curvature and torsion for the curves in R3, it will govern the local properties of that curve. Okay, so the formal statement is that suppose you have considered, suppose alpha and alpha bar be two unit speed parameterized curve in R3 with the same curvature kappa greater than 0 and the same torsion. So, then you can find out a rigid motion. I'll define it. What does it mean by rigid motion? AM of R3 such that you can obtain this alpha bar from alpha by through this rigid motion M. That means alpha bar will be M composed with alpha. Okay. On the other hand, suppose suppose you have two smooth functions. One is kappa greater than 0 everywhere and tau. So given two smooth functions, kappa which is greater than 0 everywhere and tau, you can construct a unit speed curve in R3 whose curvature coincides with kappa and the torsion will be tau. Okay, so this theorem reveals the fact that these two geometrical entities will completely govern the local behavior of these kind of curves. Okay, so before proving this theorem, we need to define what does it mean by a rigid motion briefly. That first of all, we will define translation by vector A. So translation means, so it will be a map. So for a vector small a in R3, this map T suffix a from R3 to R3 defined by TA of x goes to x plus a, and this is called the translation by this vector a. Okay. And another map is called orthogonal transformation. So this is defined denoted by r suffix theta, and it is defined to be a linear map. The linear map which satisfies satisfying this property, that is, if you take two vector x and y and you take the dot product of their images, then this will be same as the dot product of the constant vectors. Okay, that means this map will preserve the distance, right? This is true for all xy belongs to. So it preserves the distance. Okay. Okay. And with the help of these two maps, that is a translation by a vector and the orthogonal transformation, we can define a rigid motion. So a rigid motion in R3 is defined to be a composition of a translation with an orthogonal transformation. Okay, that means that is M from R3 to R3 is defined to be a rigid motion if it is something like this, that is TA compose some r theta. Okay, having orthogonal transformation, we should take with positive determinant. Okay, and you will observe that. So this kind of map will give you some information that if you take a smooth parametric curve alpha, suppose alpha, a smooth parametric curve, then you will see that the rigid motion, if you apply a rigid motion to this curve, then it will preserve the arc length. Okay, so a rigid motion in R3 will preserve the arc length. That's because if you want to compute the the first derivative of this composition, then you will arrive at, so this will be something like this. So it is kind of r theta alpha t plus a dashed, right? So therefore, so it is actually r theta alpha dash t. Okay. Now taking the norm, so this will be the norm of r theta alpha dash t, and since it preserves distance, so it will be norm of this one, right? So with the help of this, you can prove this one, and this kind of map will also have, so you can also prove that the curvature of a smooth parameterized curve is invariant under the action of rigid motions. And similarly, if you are thinking of torsion, so that is also, that will satisfy the same property. That is, the torsion also the torsion of a smooth parameterized curve. Yeah. Without having singular points of order 1 is also invariant under rigid motions. So these are left as an exercise. Okay. Now, so this is the right time to prove this theorem, fundamental theorem of space curves. So let us start. So proof of theorem. So what is the scheme? So let us fix a point in the interval. Suppose you take S naught fixed. Okay. Now you can consider the orthonormal basis of R3 corresponding to each given curve, that is alpha and alpha bar. Suppose for alpha, your penetrator is T S naught, eta S naught, B S naught, and for your curve alpha bar, so this is your T bar S naught eta bar S naught B bar S naught. Okay. And after getting these two orthonormal bases of R3, what you can do, you can construct a rotation, you can construct a map, a rotation. So these are called rotation matrices. So these are theta about the origin of R3, which takes the basis T S naught, eta S naught, B S naught onto T bar S naught, eta bar S naught, B bar S naught. So that takes the basis T S naught, this onto this one. And after executing this process, you can make a translation which takes alpha S naught to alpha bar S naught, right? So yeah. Now make a translation. So now make a translation that takes alpha bar is not to alpha is not to alpha bar is not. So this says that by means of a rigid motion, you can be able to assume that. So we can now assume that by means of a rigid motion, so assume that these are equal just by using a rigid motion. Okay. So at the point S naught, you can assume this. Okay. And now you can apply the Frenet triadron for any S. That means you can so for any S, your Frenet triadron will satisfy. That means for alpha it will be T eta B, and for this is for alpha, and T bar eta bar B bar, this is for alpha bar. Okay. Then these orthonormal bases for any S will satisfy the Frenet formulae. That means T dashed is kappa eta, eta dashed is minus kappa T plus tau B, and your B dashed is minus tau eta. Similarly, for the curve alpha bar, your T bar dashed is kappa eta bar, because you have assumed that the curves have the same curvature, right? So this is eta bar dashed is minus kappa T bar plus tau B bar, and your V bar dashed is minus tau eta bar. Okay. So this is for the curve alpha, and this is for the curve alpha bar, subject to the assumption that we have made above. Okay. Now one can define, so you can introduce a map T from the interval I R by this definition, that is T of S is T bar S Ts plus eta bar S eta S plus B bar S ds for all S belongs to I. Then you will find that number one, at the point S naught, this Ts naught is, since this T bar and T are equal, eta bar and eta are equal, B bar and B are equal at the point S naught, so this will give you 3. Also, for any S, you can say that T bar Ts, this will be less or equal to 1. Eta bar S dot eta S, it is also less or equal to 1, and B bar S, yes, less or equal to 1. Check. And the equality holds, that is T bar S dot Ts equals to 1 if and only if these are same. And the same thing will happen for other two vectors, that is eta bar S dot eta S, this is also 1 if and only if it is eta is equal to eta bar, and B bar S dot Bs equal to 1 if and only if B equal to this one. Okay. So these are easy stuff, so you can check on your own. Okay. And in view of these above properties, so for all S, your Ts is actually less or equal to 3, and the equality holds if and only if your T equal to T bar, eta equal to eta bar, and B equal to B bar, right? Now using this, we would like to compute T dashed S. And after computing this T dashed S and applying the Serret-Frenet formulae for both the Frenet triadrans, so you can easily get that this is going to be 0. This is true for all. For all S belongs to I. And therefore, this T, so this T is a constant over I. Okay. Now, since t is a constant over I, and you have already shown that at the point S naught, T S naught is 3. So this means T of S equals with 3 for all S belongs to I. And then from this one, you can conclude that the vectors T, eta, and B coincides with T bar, eta bar, and B bar. Okay. And now from this equation, T equal to T bar, just taking so T, what is T? T is alpha dash S, and what is T bar? Alpha bar dash S. And since it is true for all S, so therefore we will have that alpha S minus alpha bar S is a constant for all S belongs to I. But again, we have already assumed above that at the point S naught, by means of the rigid motion, alpha S naught is alpha S, alpha bar S naught, right? So since alpha S naught equals with alpha bar S naught, so this shows that, and since this is constant for all S, so you can make an assertion that alpha S is going to be alpha bar S for all S belongs to I. So by means of a rigid motion, so this alpha bar can be achieved from alpha through a rigid motion. Okay. Okay. So this proves actually the uniqueness of alpha and alpha bar, of existence of alpha and alpha bar having the same curvature and torsion up to a rigid motion. Okay. Now let us move on to the converse part. That means that we have assumed that, so converse part, so the given two smooth functions kappa and tau having satisfied the Seret-Frenet formula that I should mention right now. Okay. So suppose that given two functions kappa and tau, which will be satisfying the Seret-Frenet formulae, that is T dashed eta dashed is and B dashed is minus tau eta. Suppose we put a numbering here 1. Okay. Then this is a system of differential equation, and with the by means of the theorem of existence and uniqueness of solutions of a differential equation, system of differential equations, one may easily say that that given an orthonormal positively oriented triedron T naught B naught at the initial point is not, you can achieve a solution, a unique solution of this above system of differential equation, that is Ts, eta s, and Bs as a triedron at each S. Okay. Okay. So positively oriented means whenever you are changing the basis, so the change of basis will have determinant positive. Okay. Okay. Subject to the, yes, I should mention it. Subject to the initial conditions that is your Ts naught is T naught, eta S naught is eta naught, and Ps naught is B naught. Okay. Okay. So now it is so you can observe that from one. So we have so this corresponds to a skew symmetric matrix, that is, so equation 1 gives you a skew symmetric matrix, that is 0 kappa 0 minus kappa 0 tau and 0 minus tau 0. And then you can prove, you can consider a problem here. With the help of this, you can say that actually so this will be a orthonormal set of vectors. Yeah, these are okay. And the problem I can write down the problem. Yeah. So suppose you have a skew symmetric matrix of order 3 cross 3 is skew symmetric matrix of order 3 cross 3 with the entries are real numbers, okay, of real numbers, and choose 3 smooth functions. Suppose V1, V2, V3, 3 smooth functions from the interval I to R3 such that each of these functions will satisfy this equation, that is Vk dot is the summation Akj Tj. That means j is 1 to 3 for all k equal to 1 to 3. So this is true for each of these functions, subject to the condition that at the initial situation, that means at some s naught, the functions v1 s naught, v2 s naught, and v3 s naught will be the orthonormal set of vectors. Set of vectors for the initial point s naught. Then you can assert that so then your conclusion will be that the solutions you are getting out of this system of differential equations is again orthonormal for all s. Okay, so let's get back to the proof again. So okay, now choose choose the orthonormal basis, the standard orthonormal basis for R3. That means suppose we denote it by I, J, and K. That means I means 1, 0, 0. As you all know, it is familiar to all of you. Okay. So, okay. And without loss of generality, we may assume that our at the initial point is not. We can assume that for the sake of convenience, your initial situation is that Ts naught is I, eta s naught is your J, and Bs naught is your K. Okay. And in view of the above problem, so we can say that the solutions that we have obtained, that is eta s, Ts, eta s, Bs, it will be orthonormal, right? Now let us define a map alpha from I to R3 by means of this integration, that is alpha s equals with is defined to be integral from s naught to s t u du. Okay. Yeah. Okay. This is true for all s. We have defined it for all s belongs to I. And then by the fundamental theorem of integral calculus, so you can easily say that, so note that So your alpha dashed S is TS. Okay. And where T is a unit vector, which implies that so norm of alpha dashed S is 1. And this means that your alpha is of unit speed. Okay. Okay. Again, by equation 1, you have that T dashed S is kappa S eta S. Okay. So where this eta is also a unit vector, and this leads to the fact that this K is eventually be, this is the curvature of this above defined alpha. Okay. Now we should move forward for the torsion. So note that again that the vector B is orthogonal to T, and the norm of this vector has been proved to be 1. And thirdly, B is orthogonal to eta also, right? So if we want to write, so B is orthogonal to T and B is orthogonal to eta. So this leads to the situation is that you can say that B can be represented as some scalar multiple of this cross product of T cross eta. Suppose you take some constant mu. Okay. Then what are the possible values of mu? So then this will be, since your norm is 1, so your mu s possibly plus minus 1. Okay. But that mu, this is a constant map on I. Okay. So starting from S naught, you will see that at the initial point Bs naught will be, as we have already defined, this K. But what is K? K is I cross J, right? That means it is Ts naught cross eta S naught. So from the initial situation, this tells you that your mu S naught must be 1. But since mu is a constant map, so mu of S is 1. And this proves that your B will be T cross eta, and this gives you the binormal vector of the curve alpha. and possibly by the equation 1, your tau is the torsion, right, of that alpha. So hence we have proved that we have obtained a curve, we have defined a curve which is of unit speed, having the curvature kappa and torsion tau. So this alpha is the required unit speed curve. Yeah. Okay, so with this one, I would like to finish my session for today.
Hello.
Hello.
Hello. Dr. Abhishek, have you finished?
Hello. Yes, I finished.
Okay. So, what is tomorrow's plan?
Tomorrow I will discuss about some local canonical forms of the curves,
Okay.
and participants have requested me to say something about curves and what is the difference between a curve and parameterized curve. So maybe I will put some light on that.
Okay. And have you shared tutorial problems to tutors?
Okay, I'll be present in the tutorial session. Okay.
Okay.
Yeah.
Please, if possible, share to them also so that they can be prepared.
Yeah, actually, I have already informed Somo and Sagar.
Oh, okay.
So, yeah. So, I think they can manage.
Okay. So, thanks for this nice session. So, now participants, we will meet in the second lecture for today at 2 p.m. So, please join on time. Thank you.
Thank you. Okay.